Select the major product of the following reaction sequence. So in this reaction, we are starting with an alcohol, and we are taking this through a two-step process. So in the first step of the reaction, we're treating this with tosyl chloride and pyridine, and then we're treating it with sodium cyanide. So alcohols can undergo substitution and elimination reactions, provided we have a way to transfer them into a good leaving group. So the alcohol itself is a very poor leaving group. It would have to leave as a hydroxide ion. So what we're doing in the first step of this is we are taking the alcohol and we are converting it into a good leaving group. So this converts your alcohol into, it's going to be a tosylate ester. So a tosylate ester, which has a good leaving group. Okay, so in our first step, we're taking our alcohol, which has a poor leaving group, and transforming it into something that has a good leaving group. And then in the second step, we have the cyanide ion, which is a good nucleophile. And so in our second step, we are going to be doing a substitution reaction. And since this is a secondary substrate, that carbon has bonds to two other carbon atoms, we're going to be looking at an SN2 substitution. So that's kind of a brief overview. What we want to do is take a look at the mechanism, because we really want to focus on the stereochemistry for this reaction, because this is really all focused on that stereochemistry. So for the first step, you have an alcohol. So there is the alcohol, and it's reacting with tosyl chloride. So tosyl chloride is a rather large structure. So we will draw it, and then afterwards we will abbreviate it with just the TS. So it is essentially this, okay? And so what we have is we have a nucleophile and we have an electrophilic sulfur. So the alcohol is acting as the nucleophile. So it is attacking this sulfur and pushing off the chlorine as a leaving group. So we have the oxygen bound to a sulfur, which still has these double bonds, and then the benzene ring. And we had a hydrogen here. That hydrogen would still be attached. So this is what the role of the pyridine is. So the tosyl chloride here, your alcohol is attacking the tosyl chloride. And this acidic hydrogen is going to be taken by pyridine. So pyridine is a base. So here is pyridine. And so the role of the pyridine is just to remove this acidic hydrogen. So that's pyridine. Okay, so the pyridine is removing that acidic hydrogen. And so then we will have the full product of that first step, which is, and I'm going to abbreviate, so this whole portion can be OTS. So we're going to abbreviate that as OTS, and we have the methyl group still. So we have taken the alcohol, we've transformed it into a good leaving group, and what's important here is that we have conserved the stereochemistry of this chiral carbon. So notice here the bond to oxygen is sticking out of the plane of the page. It still is in our sulfonate ester in this tosylate. And that's because at no point in this mechanism was that chiral carbon involved. So up until here, nothing has happened to that carbon, so the bonds should still be where they started at. So that means the bond to oxygen sticking out of the plane of the page. So now that we've got a good leaving group, so the tosylate is a good leaving group, in your second step, you have a good nucleophile, the cyanide ion, that can do an SN2 attack. So we can draw our cyanide ion. And so an SN2 is your concerted substitution. So essentially this nucleophile has got to come in from the opposite face of the leaving group. So it's kind of sneaking up behind the leaving group and pushing it out of the way. So this cyanide ion is going to come in and attack that electrophilic carbon and push off that leaving group. And since it's approaching from the opposite face, the tosylate was sticking out of the plane. That means the cyano group that we're adding is going to be going into the plane of the page, which corresponds with option C.